I'm currently the chair of the physics department, and I want to welcome you all to this symposium in honor of Jim Gunton. As you see from the program, we have a very dense packed program here with three outstanding speakers who each will give about a half an hour presentation related to their work and their relation to Jim's work. And my duty is here only to welcome you, and I want to ask Dimitri Babylonis to say a few words about Jim Gunton's academic and research career.
Thank you all for coming to the symposium. I'd also like to thank the speakers for coming to honor Jim's contribution to statistical physics. So I would like to say a few words about Jim's career. And all of this I was able to find out in a meeting we had this year in Santa Fe, were organized by one of his former postdocs, Albert Saxena. He, on the occasion of his 80th birthday, you can see how many colleagues and friends of James came to this meeting. So James started BA in chemistry at Lehigh College in Oregon, and then he moved as a Rhodes Scholar, moved to Oxford, where he met, and during his early years, he met many well-known physicists with whom he still has close relationship. And then moved to, after that, went to Stanford to get his PhD. There he met with the Stein, Ted Burkhardt, Jeff West, Mike Zake, who were shown here at the Santa Fe meeting. So his first position was in the University of Western Australia for 2 years, and then before moving to Temple University. And during that time, his first work was in the critical phenomena. You can see here the title of his first paper, Behavior of Correlation Function. At that time, at Temple, he met and collaborated with many well-known people in statistical mechanics, like Mel Green, and especially Theodore, with whom he wrote several papers. Both are well-known Kawasaki quantum field operator presented in his paper described general behavioral systems away from thermal equilibrium. And during that time, he visited Dr. Kawasaki many times in Japan. Dr. Kawasaki was planning to come here, and I met him this summer in Japan, in Fukuoka. As you can see, he had a broken bone in his back, and he had not recovered yet, so that's why he was not able to come participate at the meeting too. But he told many stories about Jim's visits to Japan. Then he started building his own group at Temple, and where he became very active. As you can see here, he became director of the Center for Advanced Computational Science and the Institute for Surface Interface Science. At that point, his group grew to many students and postdocs. Some of you see here, he was publishing about 15 papers per year at some point. And talking about his contributions, you can see here how many alumni from his group, these are probably not, for sure, not all of them, have moved on to have leading positions in academia and are leaders in statistical mechanics and related areas. Then he took the next step to become a dean at Lehigh University. There's Jim. And then at that point, before, let me tell a few words about his work at Temple. He moved to studies now of phase transitions, path information, nonlinear systems, finite size effects, computer simulations, especially, and combining both studies of model systems and applied actual applications. These are two of his very cited papers, and a photo with some of his colleagues from Temple 30 years later. Now here's the dean at Lehigh. Despite his administrative responsibilities, he kept publishing papers, mostly with his former collaborators, and on topics such as polymer phase separation and special temporal chaos. Then, after a one-year position as a provost at Kenyon College, he came back to our department where he started to supervise physics students and postdocs, and focused now on applications of statistical mechanics to biological systems, the condensation of proteins, the form crystals, self-assembly of colloidal particles, and still working on topics that have to do with heterogeneity and noise. And he had a very fruitful collaboration with Jeff Rickman at Lehigh University. This is some highlights from his work at Lehigh, a book on protein condensation, a cartoon of colloidal aggregation by Wei Li. And many students and postdocs also worked with him over these years. Many of them are in academia, others moved to other positions. And he actually still has 3 graduate students, some here with red color, of course, still working with him on related topics. So with those years, the department started to develop strength in biophysics. Here with Professor Daniel Yang, they worked together. They are our department from about the same time. They were the chairs of my chess committee. I came here in 2006. We hired another biophysicist last year. All this work, I mean, it's amazing to think about. In Santa Fe, Professor Vinales and Raul Doral assembled all of Jim's papers into 3 volumes. So there's Jim happy and Barstow the happy. So with this, I'd like to thank Jim for everything he's done in science, and I'd like to invite you, Jim, to say a few words.
Thank you very much, Dimitri. Originally, when I was planning my talk, I thought I would make a few stories about some of the speakers today, but I have no story to tell about Professor Widom, so I decided to keep my stories to myself. If any of you are interested, I will tell you them later. So I'll keep this brief so we can stay on time. Do I need this? I can move people out of the room, so. I'll just keep this very brief. First of all, I want to thank the department for hosting this event. I certainly never expected this to happen, and I can tell you from the depths of my heart that I'm deeply touched by it. So thank you all very much. I want to particularly thank the organizers of the conference, of the symposium, and particularly Dimitri Vavilonis for all the hard work that's been in getting this together and for inviting these distinguished speakers to come. Finally, I want to thank Professor Widom, Professor Burkhardt, and Professor Swendsen for agreeing to come and speak here. They're all very distinguished scientists, and I am honored to have them here today. And lastly, I would like to thank all of you for coming. So I hope you can enjoy the remaining part of the program. Thank you very much.
So it's my honor to introduce Professor Widom, who is the Emeritus Goldman Smith Professor of Chemistry at Cornell University. Professor Widom got his degree at Columbia University and his PhD degree at Cornell in 1953, where he became an instructor and then associate professor in 1955, and he has been there at Cornell ever since, chairing the chemistry department between 1978 and 1981. He has made groundbreaking contributions to statistical mechanics, for which he was an elected member of the National Academy of Sciences and a fellow of the American Academy of Arts and Sciences, plus many other honors. He has received the Boltzmann Medal, and I'll quote here from the award for his illuminated studies of the statistical mechanics of fluids and fluid mixtures and their interfacial properties, especially the clear and general formulation of scaling hypothesis for the equation of state and surface tensors of fluids in their critical point. I don't have anything to say about this video, so please.
Thank you very much, Professor Vavlo. And thank you, Jim, for, to quote Yogi Berra, thank you for making this occasion necessary. So I'm going to start by telling you how I first came to know Jim's work, and also what an important place it had in the lectures that I used to give in statistical mechanics. So there's the paper that was already referred to, the paper that he wrote with Buckingham, and he kindly sent me a reprint of it. And you see this red asterisk up here. That is his handwriting, and he put that red asterisk in to refer to a footnote that he then wrote in his own writing down at the bottom of the page. It says Department of Physics, Temple University. That's because this showed that he had been at Western Australia. He wanted to let me know that he had moved. And of course, as we heard, that's only part of the history. He then, after some years, moved to Lehigh, where he is now. And that paper was a wonderful example of an exactly soluble model of critical phenomena and of the dependence of the critical phenomena on the physical dimensions of the space in which it was taking part. And that became so illuminating that it was then one of the showpieces of my statistical mechanics lectures. And I'm going to show you a couple of pages from my lecture notes. They're not very elegant because it was never my intention that they be shown in public. So they're just those scribbles that were intended to remind me of what it is that I wanted to put on the blackboard. The blackboard, yes, the blackboard during my statistical mechanics lectures. And here you see the chemical potential of the ideal Bose gas in units of the thermal energy kT, written as a function of the product of the density and the dimensionality power. D is the dimension of space, the dimensionality power of the thermal de Broglie wavelength. And this says that because a certain integral diverges at y equals 0, that if the dimensionality is less than or equal to 2, there is no phase transition. This is a perfectly smooth curve, giving the chemical potential as a function of the scaling of the scale density. But as soon as the dimensionality exceeds 2, and as long as it's less than 4, then you see a critical phenomenon where you see that this curve, in case d equal 3, which is the intermediate dimensionality, so that's intermediate between the 2 and 4, that means this will be parabolic, because then d is equal to 4, half is 4, and d is equal to 3. And so that's 1.5 minus 1, the 1/2 power. So that says that this scaling variable, rho times lambda to the d, is parabolic in the chemical potential. And then it reaches this point, but the parabola can't continue, because if that parabola continued, so this curve began to come down again, that would say that the chemical potential is decreasing with increasing density, and that violates a thermodynamic stability condition. And this system knows that very well, so instead of coming down, continuing the parabola, what it does is just pile the excess density into the ground state, and that's the well-known condensation in the ideal Bose gas. So that's where dimensionality lie between 2 and 4, but that's not the end. So in dimensionality 4, when the dimensionality is 4, there is Jim's famous logarithm. That was the logarithmic singularity that occurs when you reach 4 dimensions, and when before 4 dimensions the behavior is showing critical phenomena, at least between 2 and 4, and then above 4 dimensions, so here we are above 4, there you see that this is just goes into the critical point linearly with the first power of the chemical potential. And this actually has had some resonance with what came many years later in the renormalization group phenomenon. There are 2 fixed points in the story. As the dimensionality increases, those fixed points approach each other. In 4 dimensions, they coincide, and then in greater than 4 dimensions, they come apart again. But when they come apart, and those two fixed points are called the critical fixed point and the mean field theory fixed point. Before 4 dimensions, they show the critical phenomena. Beyond 4 dimensions, it's the mean field theory. Now, these singularities that were present before 4 dimensions have not disappeared when the dimensionality exceeds 4. It's just that they've become subdominant, and it's exactly the same story in the theory in Wilson's theory, where when the coinciding fixed points at 4 dimensions recede from each other, and the mean field fixed point then becomes a dominant one. The other fixed point remains, just as these singular points also remain when the dimensionality is greater than 4, but they don't show up to leading order. That is, they become subdominant. So, and this was as far as I know, the first and probably nicest example of that phenomenon occurring. So we owe all that to Jim. And then sometime later, with my co-author John Rowlandson, we wrote a book on interfacial phenomena, and we called it Molecular Theory of Capillarity. So a nice 18th century title to it, and it had a large section on critical phenomena occurring in interfaces, the behavior of surface tension and its critical singularities at critical points. And we went into that story in that chapter of our book. We went into that story about how the nature of the critical point depends on the dimensionality of space. And at one point, and that's of course quite a mysterious story, but it was illuminated by the paper of Gunton and Buckingham. And so we then said that a simple example of this being the strange dimensionality dependence of critical behavior, a simple example of this, which makes clear the mathematical mechanism by which it occurs, is seen in the ideal Bose gas, which provides an exactly soluble model of a critical point. Superscript 21, reference 21. You turn to the list of references at the end of the chapter, and that's the Gunton-Buckingham reference. So this paper has then had a very important part in our expositions of critical phenomena, both in that book and in my statistical mechanics lectures. But now I'm going to change the subject. Now I want to talk about something that again, the critical phenomena in interfaces, that is essentially in the surface tension, related to what we had been what is the book that I had written with John Rowlandson is all about. But this is very much more recent work that I've done with my collaborator Ken Koga from Okayama University in Japan. And let me first just remind people, or tell you if you're not already familiar with it, about what a tricritical point is. So imagine a multi-component liquid mixture that separates into three phases. So we have a lot of different components, minimum of three. In the experiments I'll be showing you, we actually had 4. And they're of such a nature that at sufficiently low temperature, they separate into 3 distinct phases. All the chemical components are present in all 3 phases, but in different compositions. And these phases are in equilibrium with each other. There's an interface between the beta and gamma phases, another interface between the alpha and beta phases. Now, with enough components in the system, there are enough degrees of freedom, enough knobs you can turn in order to go to a condition. I keep losing the button here. Where you can go to a condition in which the interface between the alpha and beta phases disappears. That is a critical phenomenon in which the alpha and beta phases, previously distinct, become identical. While these phases are still in equilibrium with a distinct phase gamma. And that's called the critical endpoint in the technical jargon in chemical thermodynamics. A critical endpoint, which is it is exactly an ordinary critical point. It itself is in no way special, except it commemorates the fact that there is a distinct phase still in equilibrium with those 2 phases that are becoming identical with each other. And so that's what we're going to call the alpha-beta critical endpoint. And still, because we have enough degrees of freedom, you can also arrange to have, instead of the alpha and beta phases going critical, have the beta and gamma phases going critical. So that we'll call the beta-gamma critical endpoint. The beta and gamma phases remaining in equilibrium with the distinct alpha phase. But nothing special about those critical points. They're ordinary critical points. On the other hand, we still have enough degrees of freedom because we have many chemical components, so we can change temperature and pressure if we need to, and change the chemical potentials of the various species by varying their concentrations and so on. There's still enough degrees of freedom so that at some special point we can get all 3 phases to become identical and to have those 2 interfaces disappearing simultaneously. And that is a tricritical point. And that is different from an ordinary critical point. So many years ago, I had a graduate student whose thesis consisted of measuring these interfacial tensions, tension of the alpha beta and the beta gamma interfaces, measuring those tensions from one critical endpoint to the other. That is going through the entire 3-phase region, from the alpha beta critical endpoint to the beta gamma critical endpoint, and all of the 3-phase equilibria in between, and making a graph showing the measured values of the beta gamma interfacial tension as a function of the alpha beta interfacial tension. Up here, where the alpha beta tension is equal to 0, so at that point, that is the alpha beta critical endpoint. Down here, where it is the beta gamma tension, that's what's plotted on the vertical axis. Down here, that's the beta gamma critical endpoint. That's where that tension is 0. In between, at a fixed temperature, We vary the various chemical compositions and so on, and make a plot through that three-phase region of how that one tension varies as a function of the other. And what I did with Ken Koga was to try to develop a simple thermodynamic model based on a thermodynamic density function, the kind that goes back all the way to van der Waals, and in the basis of that model to see if we could understand what's happening here in these with these experimental data and interpret them in terms of that model. Now, as I said, this entire transit through the three-phase region, from one critical endpoint to the other critical endpoint, all of that is occurring at a single temperature. Now, if you do this, and these data, the ones I'm showing you, are at temperature close to room temperature. The tricritical point that we'll be talking about in a moment, where both tensions, both the alpha beta and the beta gamma tension are simultaneously vanishing. That tricritical point is at a temperature 49 or 50 degrees, so well above room temperature. But as you were approaching the tricritical point, you wouldn't see any difference in the shape of that curve. In fact, if you didn't see what the values of the tensions are on these two axes, you wouldn't know one of those curves from another. That is, you maintain the shape of the curve as the temperature varies and approaches the tricritical point. And that was one of the things that we wanted to understand on the basis of this density functional model. So here's a picture. What I should explain, because of the large number of chemical components that we have in the system, we are basically in a four-dimensional thermodynamic space. I'm not now talking about the dimension of the space in which we live, but the thermodynamic space is four-dimensional, and that means that the tricritical point is a single unique point in that four-dimensional space. And what I'm going to show you here is what happens in two dimensions when we just take the four-dimensional figure and simply map it down into a two-dimensional plane. Oops, I went the wrong direction. Oh, yes, this was, sorry, that's because I skipped something when I was telling you about the reference to Gunton and Buckingham in that book that we wrote. This was this integral is the integral of the Bose-Einstein distribution law, and it's essentially what I was calling the product of the density by the d power of the d power of the chemical potential. Okay, so I keep pushing the wrong button. Okay, so we're in this four-dimensional thermodynamic space, but everything has been put down into two dimensions. But we still have four variables at our disposal. And here's a picture in which we have the alpha, beta, and gamma phases shown in a space in which there are four variables. Those four variables are two densities, so this is the rho 1, rho 2. This is the two-dimensional rho 1, rho 2 space, but we still have two more degrees of freedom because we have four altogether, and those are the rho 1 and rho 2 are so-called density variables, and now we have two field variables. We have one that we call T1, having the value 0 at the tricritical point, but otherwise non-zero. You can think of that as a temperature variable. And then another field variable, it could be some combination of the chemical potentials of the various constituents. That we call T2. And down in this rho 1, rho 2 plane, here's the alpha phase, there's the beta phase, there's the gamma phase, and the location of the beta phase varies along this parabolic path. When it coincides with alpha, that's the alpha-beta critical endpoint. When it corresponds with, when it coincides with gamma, that's the beta-gamma critical endpoint. But the tricritical point, that T1 will be equal to 0, and this entire triangle will have collapsed to a single point in the origin of that space. And then I will not concern you with the details, but we then specify a particular simple density functional. We then evaluate the interfacial tensions from that by minimizing the integral of that free energy functional. This again goes back to van der Waals. This is not van der Waals' free energy density, but the idea goes back to van der Waals. And then we make a plot trying to imitate the plot of the experiments that I had mentioned, where we plot one of the interfacial tensions as a function of the other from one critical endpoint to the other, going through the three-phase region. And here we are, looking at the first figure. We made this plot. This is supposed to look like the experiment. You see, it doesn't look anything like those experimental data. But notice that this is a value of T1, which you can think of as the temperature deviation from the tricritical point temperature. That's a rather large value. That is, we're still far from the tricritical point. Now we're going to get a little closer. Now we'll let T1 equal 2/3. Then this whole thing has flattened out. And then finally, we let T1 be less than 2/3. Now we produce a curve that looks just like the experimental curve. And furthermore, we can compare the quantitative aspects of this curve to the quantitative aspects we saw before. We can ask, how is a function of the distance from the tricritical point, how does the distance between this midpoint of the curve vary from the origin, which would be the tricritical point? What is the degree of tangency of this curve to the two axes, and so on? And of course, the measurements are not infinitely precise, but within the errors of the measurements, we were able to account for this. And furthermore, again, if I didn't label the values of at least two critical endpoints, the values of the tensions, you wouldn't be able to distinguish one of these curves from another. That is, they maintain all the way to the tricritical point. They maintain this shape and maintain the original scale. Okay, there's just one more thing that I wanted to talk about. This is a hand-drawn version of what it is that I'm going to tell you about. I have a more professional-looking version of that figure here, but I have an associate who told me that the one that I drew by hand is more charming. So I'm going to go back and we'll talk about it from this picture. So here, what I am showing is the locus of the alpha-beta critical endpoints. I'm now in the space of the two field variables, T1 and T2. T1 equals 0 is the tricritical point, so that's down here at the origin. And along here, with varying temperature, are all the alpha-beta critical endpoints. And the locus in this plane of the beta-gamma critical endpoints is this line. They're just lines in our theoretical model. Of course, in real life, they would probably be curves of some kind. And everything in the angle between those two critical endpoint loci, that is the region of three-phase coexistence. Any point inside that angle, any point inside this angle is a condition of three-phase equilibrium. But you see here a hyperbolic locus that has as its asymptotes those two critical endpoint lines. And that seems to be marking out in this three-phase region two different distinct aspects of that three-phase region. Some of those three-phase equilibria lie in this blank region, and some lie in this blue-hatched region. And the way in those they distinguish each other is in a phase transition occurring in the alpha-gamma interface. That is, when the beta phase, when the beta phase is either not present or is in any case not spread across the alpha and gamma phases, then that interface itself, the alpha and gamma phases meet each other, and there's a phase transition occurring in that interface. And what's happening at that phase transition? Suppose we have three liquid phases in equilibrium with each other. One possibility is that one of these phases is a globule sitting at the alpha-gamma interface. And under those circumstances, one says that the beta phase, the globule sitting there, that beta phase has not spread at the alpha-gamma interface. Another possibility is that it does spread. The condition when it is spread between the alpha and gamma is called wetting. One says that the beta phase wets the alpha-gamma interface. But when it sits as a discrete droplet and does not spread, then we say that it does not wet. And what this hyperbola does is block out the region. In this upper region, the beta phase does not wet the alpha-gamma interface. In the lower region, it does wet the alpha-gamma interface. And there's a transition in the structure of that alpha-gamma interface between having and not having the beta phase as a sandwich filling between them. And that phase transition is occurring along this hyperbolic locus. But the significance of this is that if you're here in this region that is clear in this drawing, and you want to approach one of the critical points, that is any point on this alpha-beta critical endpoint locus or any point on the beta-gamma locus, you inevitably cross that phase transition line. The only way of getting to a critical point is in the interfacial properties is to have a wetting transition occur before you reach the critical point. And this illustrates what many years ago was a wonderful discovery by John Kahn, which he called critical point wetting. And he was the first to make the observation, so far as I know, he was the first to make the observation that even if you have a three-phase equilibrium, the middle phase is not wetting the interface between the top and bottom phase. That nevertheless, on approach to a critical point, you cannot reach a critical point without that interface having undergone that wetting transition. And that middle phase will surely wet the interface between the other two somewhere before you reach that critical point. Any of the critical points on any of those sides. Okay, so that's my story, and it remains for me only to congratulate Jim on your great career and on your retirement. And judging from my own experience, retired is a great thing to be, and I wish you much joy.
Are there any questions?
Surface tension alpha beta vanishes, and I thought probably both the alpha beta and the beta gamma surface tension would vanish.
That's correct.
I see that. I didn't see that in the figures.
You remember these two lines that let me go back to that figure. Oh, it's still up there. Okay. These two lines are the lines of the alpha beta and beta gamma critical points. And they make a confluence, these two lines make a confluence at the tricritical point. So if you want those two interfacial tensions, the alpha beta and the beta gamma tension, to vanish simultaneously, then the only places where those two lines meet, and that's at the tricritical point, and that's where those two tensions are vanishing simultaneously. Did that answer your question?
I guess it does.
Okay.
I was thinking about the original diagram where sigma alpha beta say is on the vertical axis and beta
Yes.
is on the horizontal.
Yes.
I would have thought those 2 points would slip toward the origin as you approach the tricritical point.
The problem is, yes, so Ted was saying that he would have expected that in the original figure showing the experimental data, that those two tensions would have the alpha beta and beta gamma tensions would both have approached 0 at the tricritical point. But remember that figure of the experimental data was at a single temperature, and that single temperature was not the tricritical point temperature. So there is no tricritical in that diagram. There is no tricritical point, and but the midpoint of that curve, as it comes closer and closer to the origin, as the temperature increases, does meet the tricritical point.
Any other questions?
So in water and oil emulsion, is there something called a Windsor 3 phase?
Oh, a Windsor 3, yes. But
Is
you're
it
going to
related
have.
to this?
I know the expression, and I used to work in that area, but I'm afraid I've now forgotten what the Windsor 3 is.
Well, Windsor 3
Is that
is
the three-phase equilibrium showing usually represented as a three-phase triangle in the composition space, or in a composition triangle or composition tetrahedron usually.
There, I think they're looking for the interfacial point to 0. Okay, so you have a
Well, they're looking for what they call ultra-low tensions. They're looking for what they call ultra-low tensions, and their tensions can be ultra-low and often are, and that's more chemistry than physics. But they're not going to be exactly 0 unless you're in the tricritical point.
If there are no more questions, let's thank again for Sweden.
Well, I have the honor of introducing our second speaker, Professor Bob Swendsen from Carnegie Mellon University. And Bob got his PhD at the University of Pennsylvania, where he was a student of Herbert Callan. Many of you, I'm sure in this room, have seen that book, Spider's Fear. And most recently, Professor Swendsen also has written a book on thermodynamics and statistical mechanics. After his graduate work, he was at IBM Zurich for a few years, and then at Carnegie Mellon University. He has made many seminal contributions in statistical physics, particularly computational statistical physics, and there are a number of techniques and methods that bear his name, from Fehrenberg-Swendsen, Swendsen-Long dynamics, all sorts of landmark work. So without any further ado, he's going to tell us a bit about sampling in Monte Carlo simulations.
Okay, thank you very much, Jeff. I must say I'm very honored to be here. I was overjoyed when I heard the invitation to come and speak at your 80th birthday and your retirement. The talk I'm going to give is really under the category of something completely different. It's not at all the type of thing that Ben was talking about. This is a story a cautionary tale of the difficulties you can work out with talking about a problem that you're very familiar with, discussing it with other people who are very familiar with it, but when you both have different areas. So this is the myth of universal acceptance ratio, 0.234. I've done a bit of work on optimizations. As you've heard, I've done work on critical points, which Jim has also worked on. I've done some work with a different kind of optimization on proteins where you have continuous variables. So, and these came to head together in 2011 when I was at a conference that Wolfgang Janka gives. It's a Leipzig conference, and at that conference, Yuko Okamoto raised the question of the validity of the claim that there was a universal ratio, acceptance ratio, number of accepted moves versus number of trial moves in Monte Carlo, and that it was 0.234. Well, this struck me as being a little bit low, and I was quite sure that it wasn't universal, but I decided to check it out, because, you see, I had never heard of this. It turned out that that was only fair that I hadn't heard of it. They had never heard of me either. So, this is the claim. Three guys, Gelman, Robertson, Gillick, they're very highly respected people in statistics. They claim that they have proven, they're mathematicians. So this is a proof. Beware mathematicians bearing proofs. That the optimal acceptance ratio for Monte Carlo, Metropolis Monte Carlo simulations of large systems has a universal value 0.234. All right. This was published in 2 papers, which are both highly cited. This one has been cited 997 times. The other one, 1,145 times. This was the most recent one I looked at. It may be higher by now, but they are very well known, very influential papers. As I say, I'd never heard of them. That's my own fault for not really looking at the statistics literature. Well, this is their claim, and I looked it over, and there are a couple of caveats that I have that you might be interested in. First caveat, their proof is only valid for a special case where you have n terms in a Hamiltonian. They've ignored the kinetic energy degrees of freedom. That's standard, that's no problem. But the potential energy is given by this function theta, which is the same for every variable xi. Well, if that's true, all the variables are statistically independent. So if you're going to simulate it, you would not simulate n variables. You would simulate one variable and multiply the answer by n. Actually, you wouldn't even do that, because if you've got a one-dimensional problem, you can do a numerical integration of the partition function, etc., and get the answer within a tiny fraction of a second on a computer. You wouldn't bother going through Monte Carlo. So that's a problem here. But all right. Anyway, that's their proof. Now I have another caveat. Metropolis doesn't really mean what you think it means. Now I know there are a lot of people here who are quite sure they know what metropolis means. I was. Well, I still do think I know what it means. But this is the usual metropolis element. You pick a variable xj, okay, out of n variables. Preferably you pick it at random, but sometimes it doesn't matter. You pick a trial move, usually in some range, delta xji, And you accept the trial move with this probability, with the Boltzmann factor, E minus beta delta E. Beta is 1 over kt. And if the move is accepted, you go to the new spot. If it's rejected, you stay where you were. Okay. That's what I always thought metropolis was. Oh, that's an important thing. Repeat many times. Now their move, their metropolis algorithm is a little bit different. They picked a trial move for n particles, for n variables. They picked every trial move at once. So x1 went this much, x2 went that much, x3 went that, all together. They picked them all. They accepted all trial moves with the usual probability, or they rejected all trial moves with that same probability. And they repeated that. Well, that's a very important difference. Because, and this is the thing, the Gilman, Gilks, and Roberts result is only valid for global update. That's much more serious, serious than the first one. Only this global update. The first one you might imagine it generalizes. This one is somewhat different. Why is that different? Well, every time they write metropolis, they mean global updating. And global updating is essentially, per se, extremely inefficient. It doesn't matter if you optimize anything. It's terrible. So because any correlation time that you measure, if you have a global updating, diverges with the number of particles, or the number of variables. So if you've got 100 variables, it's up by a factor of 100. If you've got 10,000, it's up by a factor of 10,000. This is a plot showing the optimal correlation time, best you can do, against number of simple harmonic oscillators, and we're going from 1 to 16. That isn't a very big system at all. But you see the total energy is the open circles. That goes up. The next one is the energy of a single oscillator down here. And the next one is the displacement. And they're all linear in the number of operators. Just as a reminder, that's the single variable updating. It doesn't matter what how many you have, the correlation time is the same. So if you're having a big system, which is the limit in which their algorithm, their proof is valid, you've got essentially a very inefficient system, a very inefficient simulation. I've got another problem with them. The third caveat is the criterion for efficiency isn't what you think it is. Now, the measurement of efficiency we know from a classical paper by Burkhardt and Binder, 1973. And when you're measuring a variable x, and it depends on the variable that you're measuring, x, you calculate the time-dependent correlation function, which is here, and you calculate a correlation time, which is the sum of time equals 1 on up, they're integers. The infinity means that you're, of course, not going to add it up completely. The time-dependent correlation function goes to 0, and after a little while, you're measuring garbage, but that you don't worry about. And the error is given by this. And you see the x variable comes in twice. The correlation function of x squared minus x average squared gets in there, and the tx, tau x, excuse me, that also depends critically on x. It's different for different variables. Now, their criterion for efficiency, they use the same criterion as Müller-Krumpar and Binder. They use the same equations without citing them, by the way. They didn't know who Müller-Krumpar and Binder are even. But they use a single particle variable for x, not a global variable like the total energy. They claim that this criterion was equivalent to every other criterion you can imagine. Do it once, it's done. It's not. If you measure something, a global quantity, you have to use a global, you get a different correlation time. And that's very crucial. Now this is a plot of optimal correlation times, optimal acceptance ratios. That's the acceptance ratio, the number of successful moves divided by the total number of moves against the size of the system. These are, again, simple harmonic oscillators. There are n of them here. Now this, let's go from the bottom up. The bottom is the open circles is displacement of a single operator. And you see the correlation time, the acceptance ratio goes down quite rapidly. And it goes to 0.234. And it really does. And for the energy of a single oscillator, that also goes to 0.234. But the energy, the acceptance ratio, the optimal acceptance ratio for the global energy is quite different. So the criterion is not a universal criterion, that the energy is, it matters that you measure the global energy and not the local energy. Now these 3 points had already been measured before they, actually we measured it for that, but those 3 points we measured before. They were measured in a paper that Buzita and all, Buzita, Kumar, and myself, we wrote that in 1991, which was substantially before their paper. And this was part of a optimization method for doing optimization of 1, 2, or 3-dimensional problems. That was important because we were interested in simulating proteins. And whenever you simulate a protein, you have highly anisotropic environments. So this direction might be very easy, but this direction is a little bit difficult. It's quite difficult. So you need to choose your move from an acceptance, from an oval, which is large in that direction and small in that direction. And that was incorporated in one bit. Now, the reason that there's a difference in the global and the local correlation times is perhaps not obvious. It was not obvious to them, of course, but it really comes up because global updating introduces time-shifted correlations, and Metropolis doesn't. So those time-shifted correlations are the problem. Now, because global updating, problems with numbers. Because global updating satisfies detail balance, whatever other values it has, the variables are correctly independent, statistically independent at the same time. So variables after a simulation at a given time are independent, but not at different times. And this leads to longer correlation times. So let me show you how this works. This is an illustration. The Monte Carlo time runs upward. So we have the bottom points first, and then we do another simulation and another one. And these are global updates as the element company are doing. Now, because this is a legitimate simulation, if I take two variables here and look at the correlations between them, they vanish. So because it satisfies detail and balance, it is a legitimate simulation. Those are statistically independent, the correlations vanish. But, now here's the same simulation. Suppose I take that variable and this variable at a different time. The correlations between those two does not vanish. And because the update at time t affects every site at time t prime, the value that xt2 has affects x3 at a later time. Now, if you try to make this quantitative, this is a picture of the average energy of particle 2 under the condition that particle 1 at time t equals 0 has an energy greater than 1/2, greater than the average value. So we're looking at the average value of T2 in that, and you see it's quite large and positive. That's with only two variables. If this is for 4 variables, this is for 8 variables. As you increase the number of variables, the effect on each one goes down. But if you have 8 variables, you've got 7 other variables that are all affected by this, and they all have that effect. So what happens is a fluctuation propagates out of the time that it occurs into the other system, the rest of the system, and then comes back eventually as a long correlation time. This is another example. This is an extreme example of how bad things can get. This is escape from a double well potential. Now it is at a temperature of 1, which means that the average energy is there. It's at 0. Okay. So the probability of these are quite large. It isn't really confined to the bottom of the well, but it's has quite an extent. So what we're going to do is to start the Monte Carlo at that point in the bottom of the right-hand side, let it run, and see what's going to happen. Now, if we try that with standard Monte Carlo with one particle being updated at the time, this takes approximately 1 or 2 moves. It goes over very, very quickly. But this way, 16 moves, 64 moves, 256, and 128 moves. 128, particles. So with this top one, you have to move all 128 at the same time, and it is very slow. This is times 10 to the 4th down here at the bottom. So basically, you cannot equilibrate this. You can't even get out of the right-hand well in a reasonable amount of time. It's pretty hopeless. We had some trouble with reviews of this. There are 2 groups that can be called on for review. The one is the statistics community, which has a very high regard for the work and a very low regard for anybody who criticizes it. And then there is people who might be in this room. And I had two referees in Physical Review E. The first one was from the statistics community, and he objected to a statement we made. There does not seem to be any practical application of the GRC result. He said it's false because it has been applied. Now, from our point of view, the keyword was practical, and the results were so inefficient that it couldn't possibly be practical. He regards it as practical if somebody has applied it to something. Our point is they shouldn't have. Now, the other one was interesting. The special acceptance ratio of 2.34 would not be taken seriously by anyone experienced in Monte Carlo simulations. The second referee, it went around again for the second referee, the second time said there are two different communities involved here. One in mathematics, one in statistical physics. A manuscript published in Physical Review A will be read by statistical physicists and not by the mathematicians who evidently need to be made aware of the fundamental issues the authors are making. Our paper was published in contrast to the 1,000 citations that the papers were criticizing. We have so far had one citation. The moral of the story is that the acceptance ratio of 0.234 is based on a valid mathematical theorem. It really is true, no comment. Difficult to do that, but it's a bad choice for Monte Carlo. If you're considering using it, caveat emptor, let the buyer beware. Thank you very much for your attention.
Are there any questions?
Yeah. So for practical systems, ones that are independent and so on.
If you like to get the simulation done in a reasonable time.
Right. Most of us at least first start with rules of thumb in terms of what the acceptance ratio should be roughly. But even though you might not be able to say what an optimal one is, because systems are different, like the anisotropic system that you mentioned, is there anything that we say about giving not even rigorous bounds, sensible bounds on acceptance ratio in general?
Yeah. Basically, for an awful lot of problems, it looks like a simple harmonic oscillator. Most things are simple harmonic oscillators, or close enough. So, for the case of the 2 or 3-dimensional anisotropic, if it's an anisotropic simple harmonic oscillator, we've got essentially an exact solution. The dynamically optimized Monte Carlo will calculate take the Monte Carlo data, calculate what the optimal ellipsoid or ellipse of values you should try, and the acceptance ratio of 1/2 is optimal for that. For other potentials, if it's really a strange potential, something like a van der Waals that goes way off this way, the optimal can be different. It can be down as low as 0.25, but you can check that, and you can see whether it really makes a difference or not. If you have a periodic potential, it's a little bit like that, and the optimal potential, the optimal ratio goes down a little bit. But
Are there any other questions? Okay, if not, let's thank you, Mr. Swendsen. speaker for today is Burkhardt. He received his PhD from Stanford University just a few months after Jim Gunton. And then he did for 15 years research in theoretical statistical mechanics in Europe, in Univ, Germany, where actually we just found out that all speakers today happen to be at the same time. And then at the Lehigh Institute in Grenoble, France. And then joined Temple University in 1981, where he has worked on critical phenomena and also related topics in polymer physics. He's a fellow of the American Physical Society, and he has received many awards for distinguished teaching, and also the Alexander von Humboldt Award for U.S. Senior Scientist. It's my honor to
Can you hear me? Am I speaking loud enough? Here's a picture of Jim at Temple University in the 1970s. And this was the golden age for statistical mechanics at Temple. Jim was the youngest member of the group. It also included Mel Green and Kiyoshi Kawasaki and Hans van Leven. I still remember Jim's disappointment when Kiyoshi, with whom he had a very fruitful collaboration, accepted a position in Japan. And yes, I met Jim in graduate school, but then I didn't see him for about 5 years till we met by accident at an APS meeting in New York, and I spent a couple of postdoctoral years, but they weren't so productive scientifically, although I had a very good time. And I was teaching at a 4-year college, and Jim invited me to spend the summer at Temple, and I was familiar with some of Ben's contributions and Kadanoff's contributions to phase transitions in critical phenomena, and then I heard that Ken Wilson had made a major breakthrough with a renormalization group for which he later got the Nobel Prize, so during the summer at Temple, I learned about this together with Jim, and it was really an enjoyable experience. There was an international conference on the renormalization group at Temple where I met other persons who were making major contributions, and this really helped me become independent in research, and it was also very enjoyable. We wrote a little paper together, and then 7 or 8 years later, I joined the faculty at Temple and had the pleasure of Jim's company for 7 or 8 years, and also of his group members on the list of the postdocs and students. That was a long list, and there was only one name I couldn't remember. Yes, here's the plan for my talk. First, I'm going to review some basic statistical properties of a freely fluctuating flexible polymer chain. And then I'm going to talk about how the fluctuations are modified when the polymer is confined in the channel. And first, I'll discuss the case of a flexible polymer. And if the channel is really narrow, then the bending energy of the polymer comes into play. It's semi-flexible, and I'll discuss those two cases. A really useful reference I found in polymer physics is the Gen's book. The Gen won the Nobel Prize in 1991, among other things, for his contributions to soft matter physics or complex fluids using very simple theoretical ideas. And yes, I wanted to show a short video given to me by Elizabeth Strapolsky, and it shows DNA fluctuating between two glass plates. Here it is, and it's not alive. It's moving just due to thermal agitation. And so you see the configuration is constantly changing, and so one question is, what is the typical size of the configuration you see, the fluctuating configuration? And you can ask, how does that typical size change if you consider longer and longer samples of DNA? And this is a question which was studied very early in polymer physics by Flory, I suppose, and others. So yes, I'm interested in the typical size or Flory radius of a fluctuating polymer chain, and yes, I'm in the good solvent region where the fluctuations basically are independent of energy, and the thermodynamics is determined by counting, not by energy considerations. And here's how the formula for the typical size varies with the number of monomers, or with the contour length of the polymer. And A is a microscopic distance, like the distance between individual monomers, and nu is a universal exponent. And so a simple model you could make is an ideal polymer model in which you just view the polymer as a random walk. And now if you make a random walk, you end up after n steps a distance of the square root of n times the step size from your starting point. And this exponent nu is universal in the sense that whether you make a random walk in a continuum or on the lattice, the exponent is the same. Now, in the polymer problem, one has excluded volume. The polymer can't loop back and fill a space which is already occupied by another portion of the polymer. So it's like a walk which is random, except that the walk can never return where it's been. And this tends to swell the polymer. The exponent nu is larger than the random walk value. And in one dimension, the exponent is 1. That's pretty easy to understand. If you're making a random walk in one dimension, but you can't return where you've been, you can only go straight ahead. So the exponent is 1. And in 2 dimensions, the number is known exactly, not by counting possibilities, but by a connection with phase transitions in magnetic systems I'll mention later. And so in 2 dimensions, you couldn't have a configuration like this, but you can in 3 dimensions if the polymer is going over or under the polymer, when it comes back. And so the exponent is larger than 3/4. It's, the best estimate at the moment from Monte Carlo simulations of walks of up to 30 million steps is this value here. There are also field theoretical estimates, and the problem of calculating this exponent exactly is comparable in difficulty maybe with solving the 3-dimensional Ising model exactly. It's a highly non-trivial problem, even though it's very easily stated. Oh yes, I'll just mention briefly a major contribution of Duchamps, and that was recognizing that the problem of the statistics of a long polymer chain is related to phase transitions in magnetic systems. So here's a model of spins on the lattice with nearest neighbor interactions, and these spins have n components. So in case n equals 3, this is just the ordinary Heisenberg model of classical spins on a lattice. And the case n equals 1, that's the Ising model. You just have one spin, the length is fixed so it can point up or down. And you can calculate the spin-spin correlation function in powers of j over kt. This is called the high temperature expansion. And it turns out that in the limit n going to 0, the spin-spin correlation function is the same as the polymer partition function. This limit n going to 0 isn't easy to picture, but it has a well-defined graphical meaning. And if you want to find the correlation function between spins at 0 and r in the magnetic model, you just draw all self-avoiding walks from 0 to r on the lattice, and you weight each of those walks with k times the number of steps in the walk. And so what do you achieve by this? Typically the spin-spin correlation function falls off exponentially with a correlation length c, and this correlation length becomes infinite at the phase point at the critical point of a phase transition. And if you use this connection between the polymer and the magnetic system, you see that this exponent nu is the same as here. So what have you gained here? Well, very powerful methods were developed in connection with phase transitions and critical phenomena. Wilson's renormalization group work, and then in 2 dimensions you have especially powerful methods like conformal invariance and Coulomb gas methods. Anyway, that exact result that nu is 3/4 in 2 dimensions comes from studying the magnetic problem. So now I want to come to the case of a polymer inserted into a channel. And I want to consider the case in which the diameter of the tube here is much less than the size of the polymer outside the channel. It's not this way in my charming hand-drawn diagram. So yes, it's entropically favorable for the polymer not to go into the channel. It can take on far more configurations outside the channel than in the channel. outside the channel, it can take on every configuration it can take on in the channel, and many, many more. So you have to do work to squeeze the polymer in the channel. And so you can ask how much work. And another question you can ask is what length of tube does the polymer fill up? So you're squeezing it down to dimension D in the vertical direction. How much does it spread out? And this is easy to answer for an incompressible object like a blob of clay, but a polymer is mostly free space, and it's quite compressible. So what length of tube does it fill up? And this sounds like a really, really difficult questions to answer. And the Jen obtained answers with a simple picture called the blob picture. So think of the polymer as a succession of blobs, each one filling up a sphere with diameter d. And within a blob, the monomers don't feel the monomers in the next blob, and they also don't feel the effects of the walls. They're within the blob. So Jen suggested an analogy with this relation outside for the unconfined polymer. Let's write this relation for within a blob, and the size of the blob is d, and this n blob, that's the number of monomers in the blob. So from this picture, you can figure out the number of monomers in the blob, and once you know the number of monomers in the blob, you can multiply that by the diameter of the blob, and then that gives you the length of the tube which is occupied. And here's the prediction. It's a beautiful prediction which only involves macroscopic quantities. It doesn't involve microscopic quantities like the monomer separation at all. And yes, we put in a dimensionless numerical factor because our arguments are rather imprecise. And so this tells us how the length depends on the diameter of the tube. Yes, if you kind of squeeze down the diameter, the length diverges as d to the minus 1/3 in 2 dimensions, and it's d to this result in 3 dimensions. And that comes from the value of the exponent nu. And b, yes, is a dimensionless number, presumably of order 1. I'll have more to say about that. Okay, yes, one thing I worked on around the year 2000 with again is checking whether the blob picture really is consistent with the mapping on the magnetic system. We know a lot about magnetic systems, and is the Shen's picture correct? And we found that it is correct, and by considering a magnetic system in the form of a bar. So it's basically a one-dimensional system. One-dimensional systems don't have phase transitions, but one has a well-developed theory of finite scaling for understanding behavior close to phase transitions. And as you make the diameter of the bar larger, then you recover a regular phase transition. And we showed that yes, the blob picture is consistent with the magnetic mapping, and also we claim that this number A is universal. I mean, it depends on the dimension, and it depends on, so this will be for polymers on the strip. Here's the result for polymers on the surface of a long cylinder. So it's a strip with periodic boundary conditions. And they're very good agreement with our results based on transfer matrix analysis and simulations. And here are predictions in 3 dimensions, which I extracted from a paper by Klushin et al. And you know, it doesn't seem to have been generally recognized that both of these variables, that both of these numbers, A and B, they're universal numbers. You know, they're in Duchenne's blob prediction. Not only is the blob prediction correct, but the numbers are universal. So there are no adjustable parameters in the blob predictions. So. Now I want to come to the case of a semi-flexible polymer in a channel. You know, polymers have bending energy, but if you have a very long polymer outside that's not confined, then it behaves essentially as if it's flexible. You can characterize a polymer by a persistence length, and that's the length over which not very much bending occurs. So if you have a polymer with length less than P, it behaves basically like a rod. And if its length is much larger than P, at least in an environment where it's not confined, then it behaves as a flexible polymer. And so here I'm considering the case in which the tube is so, yes, the diameter of the tube is less than the persistence length. The diameter is much less than the persistence length. So you don't have overhangs. The bending energy keeps the polymer from looping back. The polymer is sort of like a wire rattling around in the tube. And yes, you know, one has done experiments with DNA and confined in nano channels, and you know, having the DNA nearly straight is convenient for genomic mapping and things like that. And I think if you try to straighten DNA by pulling at the ends, it ruptures. But in a tube, it naturally straightens without the need for tension. So this is promising for applications in bioengineering and biological science. And now for, O'Dyke presented an intuitive picture. O'Dyke is a physicist still active in Holland, and it goes this way. In O'Dyke's picture, what plays the role of a glob is the section of polymer between two consecutive deflections from the wall of the tube. You can think of the polymer as being made up of sections like that. And just as we wrote in the flexible case, I forgot to discuss the free energy, but it goes, this is the free energy per length, it goes as kT over lambda. You know, this free energy per unit length, well, we can compute it for a single section. It's free energy kT divided by the length. And clearly the horizontal length of the polymer is less than the contour length, a little less, not too much. And you can work out an expression for the difference just using the Pythagorean theorem, thinking of this as a triangle, and theta here is some average angle. You know, yes, it would be d over lambda if you had a triangle here. But to get further than this, we need to know how large is lambda? How does it depend on the physical parameters of the system. And you can, O'Donnell argued this way, yes, the polymer has a bending energy, so it's energetically favorable for the slope to be constant. But they're thermal fluctuations, so the slope is making a random walk. The slope is making a random walk. The change in slope, typical change, is growing as t to the 1/2 as you go a distance t down the tube. T isn't time, it's distance along the tube. And if you integrate this, you find that the transverse displacement, the drift to the side, grows as t to the 3/2. So let's now apply this relation to this segment here. For the displacement to the side, we put d. For the time, we put this length. And we see then that lambda goes as d to the 2/3. But by dimensional consistency, lambda's a length, we need another length of 1/3. And that's the persistence length. So that gives us then formulas for the free energy, the work you need to do to squeeze the polymer in the tube, and the length of tube it occupies. And one approach to try. Yes, I was interested in the values of these parameters, and so you can write down the Hamiltonian. The simplest Hamiltonian you can assume is kind of Hooke's law Hamiltonian. If I write it in terms of a transverse dimension and a dimension t down the tube, you can write it this way. And this is for a polymer in 2 dimensions. For a polymer in 3 dimensions, you have another term like this involving y instead of x. And this is just the energy you would write for the energy of vibrations of an elastic rod. If you were an engineer and were calculating the rate at which a rod vibrates back and forth, you would use this Hamiltonian. One can show that the partition function then obeys this differential equation. So one approach is to try to solve the differential equation. I worked on that. Yes, you can also make very accurate simulations and using a mapping on a much simpler problem. And that is the problem of a particle moving due to random forces. So here's Newton's law for a particle subject with mass 1, subject to a random force. And at every instance of time, this force is different. And it's, say, Gaussian distributed strength. It can be positive or negative. So the particle is being buffeted by a random force. And let's consider the motion of the particle in 2 dimensions. So it starts here, and under the action of the random force, maybe after a certain time, it ends up here. Now let's make a graph of its position as a function of time. So that's a plot involving x and y and t. And here I've drawn the plot. Here, yes, we have x and y in the transverse direction and t in this direction. And as long as the randomly accelerated particle stays in this disk, it corresponds to a polymer in the tube. There's a 1-1 correspondence between the trajectory of a randomly accelerated particle and the configuration of a particle in the tube. And this is exact for a tightly confined polymer. And this is a very easy problem to simulate the motion. So you can calculate those numbers, those missing numbers in O'Dyke's picture with good precision. And here some of the results. This result for a rectangle rectangular channel with an arbitrary rectangular cross section. I worked out it took me about 6 months to get this number by solving an integral equation. It was an analytic approach, but I had to solve an integral equation. And then at one point I spent a semester in Grenoble, and over coffee I met Dominique Bicou, who just happened to have experience with random acceleration and simulations. And I told her about my calculation and that it was long involved and nobody had ever checked it. Well, an hour after coffee, he came to my office and said, well, I checked your number very quickly, and it's certainly accurate to a percent or two, maybe even better. And so this changed the way I viewed simulations. And he got the number for a tube with a circular cross section. I could only do the rectangular one. And then later in Jülich with Yin, a very smart girl who was doing her PhD thesis, we got much more accurate values. And one problem with the simulations is that after a while, the randomly accelerated particle leaves this circular domain, and then it doesn't correspond to a polymer anymore. So if you want results for long chains, well, you're not very likely to get them. But there are tricks to around this problem. And the probability the particle stays in the circular domain decays exponentially with time, and this decay constant is just the free energy divided by kT. So anyway, these are yes, for both the Odite regime where you have a stiff polymer, and for the de Gennes blob regime, we know all the numbers, and these regimes aren't so easy to realize experimentally. Of course, one is interested not just in being much less than p and being much greater than p, but the whole range of parameters. And one, yes, this is an active field, just exploring the whole range of parameters, but these numbers are serving as useful guideposts, for checking Monte Carlo simulations, and so that's one of the things I've been working on in the last many years, and I think I'll stop at this point and offer again my congratulations to Jim, wish him the best, and I'll try to answer questions.
Are there any questions?
I have more of a history question. So the early paper by de Gennes that you were talking about, was it a few years after Kavanagh's famous paper where he was essentially working out renormalization with spins, or were they at the same time?
Let's see, I think de Gennes did this around 1973. Yes, I think he certainly was familiar with developments, but his picture makes no reference to that. And yes, de Gennes often worked just from a picture. And yes, he said it once, or wrote somewhere, that there's nothing so complicated that it can't be understood, at least qualitatively. But his pictures weren't always right. He for the case of polymer absorption, he predicted an exponent which turns out to be wrong. I have a slide about this, but I think maybe would have been here long enough.
If you have a lot of polymer chains like in a belt, I guess people, if I remember, look at that in terms of sort of approximate cylinders in which they're defined, just as a way of dealing with it. So do these results, I realize they're rigorous for one polymer and one confinement, but do they help you understand polymer results?
Well, I think maybe the blob picture does, but the detailed results, and certainly the numbers I've worked out are irrelevant for something like that. Yes?
So I am confused with the similarity between the polymer in the tube and the Brownian motion within the circle.
It isn't Brownian motion, it's integrated Brownian motion.
Okay.
You know, if the acceleration is random, the velocity makes a random walk, and the position is the integral of the velocity. So it's a smoother motion than Brownian motion.
But wouldn't it be more correct to consider either, instead of white noise, color noise, to take into account the persistent length?
Let's see. The persistence length does enter there, and it enters into the correlations of the random force with itself. It enters in the strength of the random force. If the random force is very strong, then the trajectory or that has more effect on the trajectory than if the force is quite weak. The case of the force quite weak corresponds to a very large persistence length. The polymer doesn't like to bend. Yeah. Yes. If the persistence length were infinite, the point, the randomly accelerated particle would just go in a straight line.
So another, to follow up on Jeff's question, another area where the block mixture is used is to calculate things like force extension here. It's pull on the chain.
Yeah.
Do your results show whether this is correct?
Let's see. Yes, this is there are lots of results on the extension of polymers, both in tubes and without. The case I looked at here is no force at the ends. Yes, this beautiful paper from the Bender group where they this is with simulations. It's what you can do with simulations. They take the polymer outside and then they just move one end gradually inward, and they find that the polymer kind of forms a flower. You have blobs inside the tube, and then the portion outside is fluctuating. And as you continue to pull the polymer in, then at one point the end jumps in, and then the polymer is entirely contaminated. It's a beautiful paper, and those results for the universal amplitudes, I got it from the results in that paper. But they don't mention whether those they don't mention the universality of those amplitudes. So I wrote to them. Yes, getting my talk ready got me interested in this question again, and so I wrote to several persons, and am also trying to interest some people in making calculations to really test this universality in detail. But there is already some good evidence for it.
Are there any other questions? Okay, let's thank Professor Burkhardt. I'd like to once again thank Jim for everything you've done to science, the Lehigh University, Temple University, and it was a great honor to get you, partner. Thank you, Jim.